Ladies and gentlemen, you are warmly welcome to the Honourable Bernard Soysa Memorial Oration 2021. It's my pleasure to invite a very special person to formally welcome the gathering in this evening. He is the General President of the Sri Lanka Association for Advancement of Science in 2021. He is also the Dean, Faculty of Technology, University of Colombo, and a Senior Professor in Physics, Professor Sumedha Jayanthi. This invitation is for you, sir.
Thank you very much, Professor Shiromi Karunaratne. Good evening, ladies and gentlemen. I hope you all can hear me. As you are aware, today is a special day where we are going to celebrate a special event, that is the Bernard Soysa Memorial Oration, which is held by the Sri Lanka Association for the Advancement of Science every other year. This event is organized by the General Research Committee of the SLAS with the support of the family of Honourable Minister late Bernard Soysa. And today I am happy to see that the oration is delivered by Professor Priyan, an eminent scholar and who is very well known to most of us. Having worked with him in some other scientific organizations and other scientific endeavors, I know the efforts and contributions that Professor Dias is making to raise the standards of science in Sri Lanka, and especially to the field of engineering by contributing to the University of Moratuwa and nationally as well. So I think I must really feel honored that under my tenure as the General President of SLAS, that a person of Professor Priyan Dias's caliber is delivering the Bernard Soysa Memorial Oration today. And thank you very much for accepting the invitation, Professor Dias. I welcome you warmly. And also I have to very warmly welcome the members of the family of late Bernard Soysa, who have been continuously supporting this special event. Then also, I have to welcome all the participants who are joining this event online, and I thank all of them very much. But I want to specially mention the efforts made by the General Research Committee of SLAS, its chairperson, Professor Chamari Hettiarachchi, and rest of the members, and all the members of the council also, and all those participants. Again, I welcome warmly for this evening. And I hope that today's event would be a wonderful and very meaningful one. So I would just request every one of you who are participating today to enjoy this evening. Thank you all very much on behalf of SLAS. Thank you.
Thank you very much, sir. General Research Committee of SLAS is privileged to have the presence of a well-known personality, a scholar, as the orator at the Honourable Bernard Soysa Memorial Oration 2021 on interdisciplinarity through analogical transposition. Thus, the well-recognized orator will be formally introduced by reading the citation by the chairperson of the General Research Committee of SLAS, Professor Chamari Hettiarachchi. She is a professor in molecular biology and biochemistry of the Department of Chemistry, University of Colombo. Over to you, madam.
Thank you, Professor Shiromi, and good evening to all of you. So it is my honor and privilege to read the citation of Professor Priyan Dias, the orator of the Honourable Bernard Soysa Memorial Oration 2021. Professor Viranjit Priyan Solomon Dias was born on 6th October 1955. Although he received his primary education from a number of schools, Starting with Agrabodhi Vidyalaya in Kantale, his entire secondary school education was at St. Thomas's College, Mount Lavinia. He entered the University of Moratuwa in 1975 and graduated in 1980 with BSc Engineering Honours degree in Civil Engineering, while also winning the UNESCO Team Gold Medal for the Best Engineering Graduate and the Kulasinghe Award for the Best Civil Engineering Graduate. He joined the academic staff of the university in 1981 as an assistant lecturer in the Department of Civil Engineering. Then he obtained a doctoral degree from Imperial College, London in 1986. He returned to the University of Moratuwa in 1986 to be confirmed in the post of lecturer. He was promoted to the grade of associate professor in 1995, full professor in 1998, and senior professor in 2006. He was the head of the Civil Engineering Department from 2007 to 2010. And he was the founder director of research for the university from 2014 to 2017 and chairman of the Senate Research Committee SRC from 2015 to 2017. He recently retired after 40 years service at the University of Moratuwa. Professor Dias was a member of National Research Council from 2005 to 2019. He has also held the Visiting Research Fellowships at the Universities of Bristol, United Kingdom, the Melbourne in Australia, and at Carnegie Mellon University in USA and the National Technical University of Athens. He is currently the president of the National Academy of Sciences of Sri Lanka. Professor Dias' initial research training was in the concrete structure and technology, an area he continues to keep in touch with, having generated highly cited work in concrete sorptivity and durability and publishing regularly on tsunami resilience and sustainability indicators. Together with his colleagues, he has helped to promote the use of alternative material in the Sri Lankan construction industry and also to develop in-country expertise for testing and diagnosis defects in structures. He was the lead structural engineer for the design review of the Colombo Lotus Tower. Professor Dias also developed the research interest in artificial intelligence applications, system methods, and engineering philosophy. He is an associate editor of Civil Engineering and Environmental System from 2007 to date and has authored a book with a Springer Nature in 2019 titled Philosophy for Engineering, Practice, Context, Ethics, Model, Failure. Professor Dias has around 150 research publications to date with a Google Scholar Edge Index of 20. He has won many research awards, including SLAS GRC Lifetime Award in 1998, the CVCD Award for Technology-Related Science in 2008, the Institution of Civil Engineers United Kingdom Overseas Award in 2006, and the Presidential Award for Research Publication on 10 separate occasions. In 2020, he was included in a database of the top 2% researchers worldwide, prepared by authors from Stanford University and elsewhere. Not only that, connection of Professor Dias to SLAS has a long history. His father, Dr. Solomon Dias, was the Section B president in 1975 or 1976. Thank you very much.
Thank you very much, madam. sometimes the pandemic situation has forced us to be different as well as to be more creative. What you see here now is the presentation of the memorial medal to our distinguished orator, Senior Professor Priyan by the General President of SLAS, Professor Sumedha Jayanith. Thank you. Next is the moment we are waiting for. My mentor, my teacher from University of Moratuwa, Senior Professor Priyan. Sir, may I have the honor and privilege of inviting you to the podium?
Thank you very much. Thank you, Shiromi, and the others also for all the nice words said about me. I'm not sure how much I deserve all of it, but I would like, first of all, to thank the Sri Lanka Association for the Advancement of Science and also the family of the Honourable Bernard Soysa for conferring upon me the signal honor of being the orator this year. So I have now a medal to show for it, which you may not be able to see because I'm actually sitting. So at these occasions, it is customary for the orator to say a few words about the person in whose honor the lecture is being delivered. And I think some words have already been said about the Honourable Bernard Soysa. Something that a lot of people remember about him was that he was the chairman of the Public Accounts Committee of Parliament for 3 successive regimes, starting in 1965 to 70, then 70 to in 64, then 65 to 70, and also 70 to 77. So that, I think, is a signal achievement in a country where people change with almost every change in government. And actually, I had the opportunity to meet Mr. Bertram Thittawala, who was Secretary General of Parliament somewhere in the 1990s, because I had to go for an interview to Parliament when we were interviewing somebody for the position of Works Engineer. And somehow the conversation got around to the Honourable Bernard Soysa, and I won't tell you exactly what Mr. Thittawala said, but because the most diplomatic way to say it is that he was saying that the people who followed the Honourable Bernard Soysa had a very hard act to follow. The reason perhaps this oration is being given in his honor is because he was made the Minister of Science and Technology and Human Resources in 1994, a post he held until his death in 1997. And as stated by Dr. R.O.B. Wijesekara, who most of us, who almost all of us scientists look up to as a great figure in the scientific community in Sri Lanka, who passed away earlier this year, who was also the first Bernard Soysa orator. In his words, he says, in the brief period he served as Minister of Science and Technology, he worked himself into the hearts of the scientists and technologists of his country. Bernard Soysa's intellectual and philosophical attitudes fitted well with their perceptions. And he was also able, as the minister, to speak at the 50th anniversary of SLAS, that was in 1994. Perhaps this sympathy towards science and technology may have been strengthened by the fact that he was the brother-in-law of Professor Priyan Soysa, another towering figure in the scientific community of Sri Lanka. She was herself General President of SLAS in 1991, and was able to make her influence in the scientific world far greater than in her field of nutrition and pediatrics through her role as Director General of NARESA from 1992 to 1997 and Chairperson of the National Science Foundation in 1998. Now, just to inject a little bit of humor into this occasion, some of you may know that Professor Priyan Soysa's brother-in-law on her side of the family was a gentleman called Dr. Riley Fernando, who actually we knew as children because they were family friends, Dr. Riley and Manuel Fernando. And it was he who was the author, the anonymous author actually, of this, rather humorous, but humorous obituary notice, right? And when I was preparing for this lecture, I realized that this obituary was placed in the 1970s, and you can read it for yourself. Those of you in my generation will probably be familiar with it. So I realized that it was written by one of Professor Priyan Soysa's brothers-in-law at a time when her other brother-in-law was actually in the government, which was being lampooned by this humorous obituary. But of politics in those days was, and nothing significant happened as a result. So let me move on. I will move on now to the title of my talk. So there are two key words in the title. One is about the concept of interdisciplinarity, and the other one is about analogy. Now, this diagram up here talks about the various interactions between disciplines in this whole process of interdisciplinarity. And these are the different definitions for those as we go down from the top to the bottom. Now, in a general way, all of these things, especially the ones on this side of the diagram, they are called interdisciplinary. But the one that actually I want to focus on is this one here, which is called a cross-disciplinary approach, where one views one discipline from the perspective of another. So I think analogy is one way of doing that. Now, let me just introduce some basic ideas about analogy. For example, when we teach engineering students about bridges, there are three basic bridge forms: a beam bridge, an arch bridge, and a suspension bridge. And we tell them that those bridge forms have been inspired by natural phenomena. There are things like this in nature that have inspired these bridge forms. So that is a kind of analogical transposition from nature to structures. Now we can get more mathematically accurate analogies if we want to, for example, look at what happens when you twist a rectangular beam like this. So we have torsional stresses in that beam that are not so easy to calculate. And one very easy analogy to use is by stretching a membrane over a cross-section of that rectangle. And when one does that, the slope of this membrane at every point will give the corresponding or will be analogical mathematically to the torsional stress at different points in the cross-section of this rectangle. So that's a different kind of analogy. There are instances where analogy can be used in design also. For example, you have here a door frame, a door, and a tap. And there are different elements of the door and the tap that can be related to each other based on the functions that they perform. And so as a result, if you want to design, for example, a new tap or a new door, one can look at the functions that are being performed by the analogical counterpart and then generate some creative designs in that way. Now, I want to present about 4 or 5 instances of analogical transposition. But I must say that, as mentioned by George Collier in 1954, this kind of analogy involves what is called plausible reasoning. It may not be strict proofs that one comes across in analogical reasoning, but analogical reasoning is important to make any creative advances in one's field. And then if we look at this comment by a classicist, G.E.R. Lloyd, he talks about Aristotle, who in one of his rare moments of appreciation of metaphor wrote in the Poetics that skill in the use of analogy was a mark of genius and cannot be taught. Now, I do not claim to be a genius, but I do commend analogy to the scientific community in order perhaps to be more creative in the kind of, discoveries that we are likely to make. It is a situation where one views one's discipline from the perspective of another discipline. So let me give you a few examples. Right. Now, these pictures in the middle show you what I do in my first year mechanics class. I try to teach students about the stability of what are called trusses, well, these assemblies of members and joints. Now, anyone who has played with a mechano set when you were young would realize that this particular assembly is not stable. It will not be able to maintain its shape. It will become stable if you connect a diagonal member like this, and it will become even more stable if you connect two diagonal members. So now the rule that governs the stability of what we call trusses. Trusses are structures like this. We have them over roofs, sometimes in factories, or sometimes even just in large halls, we have these kinds of trusses, and we can have different kinds of trusses. So if the number of members is equal to twice the number of joints minus 3, that truss becomes what is called a simply stiff truss. Now, if you look at two trusses like this one is called a Warren truss and this one is called a fan type truss. Which one of these trusses is better connected? They are both simply stiff. They both obey this rule. Now, these kinds of questions become important because these structures like this and others are subject to what are called unforeseen loading. So if you want to have structures that are better at countering unforeseen loading, they need to be ones that are better connected, right? So clearly this one is better connected than this because this has more members than given by this law. But both of these actually have the same number of members given by this law. So how can we decide between them? Now, we look to something from network theory, itself derived from a graph theory that was developed many centuries ago by Leonhard Euler. And we look at what is called the betweenness of these elements. So if you have 4 joints that are connected like this, and if you think about any one of those points and try to go to the other points, you think about the shortest paths from which you can go to, by which you can go from A to B, C, and D. And you can see here that this particular path is traversed 3 times in that process. Now, if you start from every single one of these joints, then this path will be traversed 6 times, but these will be traversed much less. So this is what a much more in-between link. So if it is more in between, that means it is less connected to the rest of the structure, as you can even see visually in this. So what we do is we can subject these 2 structures to this kind of analysis, discover the most connected elements, and we can remove those. So what is left is the rest of the elements. The thickness of these elements is proportional to the betweenness, and we can calculate an index called relative betweenness, which equals the betweenness of the element that was removed divided by the total betweenness of the elements that are left. So if we use that rule in this example, we find that the relative betweenness of this is 5.32, whereas this one it is 15.57. So this has a much lower relative betweenness. And remember, if the betweenness is high, it means that this is less connected. So this one is a better connected truss. We can also use, so we can also borrow, just as we borrow from network theory, we can also borrow from what is called root structure analysis, where, with respect to these roads, we have 3 concepts called continuity, connectivity, and depth. And we can use the same kind of approach where these trusses are concerned, but that particular rule does not give such a difference between these 2 trusses. So even if we were to look at this truss, this one does in fact seem better connected because all the internal members are connected at both ends to these external members. But we do not, we intuitively, we can feel that, but if we apply network theory, we have actually a number by which to compare it. So as we can see that we are looking at trusses and roads, and we are borrowing from another dimension, that is from Newman's network theory, in order to come to some kind of conclusions about that. Another idea that we can have is to apply these to roads, because whether it is a truss or whether it is a road, in some ways you can consider both of these as networks. So here what you find the road network of Sri Lanka, well, only the class A roads. And what we do is we find the most in-between link at every stage in this analysis. And then based on route structure analysis, we calculate the relative connectivity and the relative depth. So here we keep removing the most connected route, and then we find that the connectivity decreases in this kind of way, whereas the relative depth increases. So it so happens that if we apply this to the road network of Sri Lanka, the most connected route is a stretch that is shared by the A6 and the A9 somewhere near Dambulla. So, you know, this could have some practical implications. I'm not saying that this is the only way by which we can decide this. But if one were to think that, you know, it is not good to have a single city of Colombo as the largest city in the country, a primate city actually, if one were to develop another city that is comparable in size, perhaps Dambulla is an area to consider. Because the fact that this route is the most in-between route means that it is the best connected to the rest of the country. And also, if you keep removing these routes, you find that the networks become disconnected like this, and they reflect, you know, almost reflect the provincial boundaries in the country. So that can either mean that the roads have followed the provincial boundaries, or that the provincial boundaries have followed the roads. So let's move on. Now here we are taking an example from management. This is systems dynamics that was developed at the MIT Sloan School of Management, and this has to do actually with you know, marketing issues. So for example, if a company has a certain number of orders, its revenue goes up, it can increase the sales force, and you find here what is called a reinforcing loop. This keeps getting better and better. But at the same time, if you have a number of orders, you know, then you may not be able to deal with it. The size of the backlog increases, your delivery time increases, there are sales difficulties, and the number of orders reduces. So this is called a balancing loop. Now, these kinds of approaches have been used even in what is called global modeling, as was done by this group for the Club of Rome somewhere in the late 1960s, which resulted in this book called The Limits to Growth, all coming out of MIT. Now, what we have done is we have transposed this system dynamics concepts to concrete durability, in which I have worked for some time. So I hope none of the buildings that you own have situations like this, where there is significant corrosion in this concrete beam. Now, there are two reasons or two causes for concrete corrosion. Concrete actually is the reinforcement is the one that corrodes. The reinforcement is naturally protected by the alkalinity of the concrete that surrounds it. But there are two ways in which that is compromised. The first one is if chloride ions penetrate this cover. So what happens is, you have these chlorides going in, perhaps in a marine environment, closer and closer to the reinforcement. If the level of chlorides builds up to a particular level, then there will be corrosion here. The corrosion products are greater than the original volume. That causes stress in the concrete, and the concrete cracks. Now, the moment the concrete cracks, there is a crack width, and the crack width actually facilitates the diffusion of chlorides into that area. Then the chloride level at the chloride amount at the level of the steel increases. That increases the corrosion current density, and even more of the steel gets corroded. So this is actually a reinforcing loop, similar to what we have here in this marketing situation. And this can be modeled in this way, and it's a very powerful way to model. Now, the actual system dynamics diagram for this situation is given here. I do not want to take you through that. But it can result, just like in these limits to growth graphs that you get here, you can provide graphs of crack width versus time in this kind of way. Now, the other way, that other cause of corrosion is actually carbonation. Now here, what happens is that the alkalinity of the concrete gets reduced because of atmospheric carbonation. And you know, the carbonation front keeps going forward like this. But in this situation, as we have also discovered through some of the experimental work that has been done here, that as the concrete layers get carbonated, their porosity gets reduced. So because their porosity gets reduced, actually here what we have done is we have measured sorptivity, which is a slightly different phenomenon, but it is connected to the diffusivity of the concrete. So the diffusion of carbon dioxide is reduced because the carbonation of concrete causes reduced porosity, and therefore diffusion of carbon dioxide is less, and this becomes a kind of balancing loop, right? So it is not a runaway situation like chloride-induced corrosion. And all civil engineers and structural engineers know that corrosion due to chlorides is much more significant than corrosion due to carbon dioxide, which is why you find that most of the structures that are corroded are fairly close to the ocean. Now, the other thing that we have included here is the effect of what is called pulverized fuel ash, which we have here. And this is also produced in our coal power plant. And this also affects this cycle like this through the various equations that are given. Let me move on. Now, we come to this idea of resilience. Now, some people think that resilience is a concept that was invented somewhere in the middle of the 20th century, especially with respect to ecosystem resilience. However, resilience is a concept that belongs to structural mechanics, and even the dictionary definitions bear that out. So if you take some kind of element like this and you pull it or push it, let's say you pull it, right? There will be a force and therefore a stress in that element, and that will cause an elongation, which actually can be represented as a strain. So we can draw what is called a stress-strain diagram. Now, the area under that stress-strain diagram in the what is called the elastic region is called resilience. After a point, most ductile materials behave in this kind of way. There is a large strain for a small increment of stress. So this is called the ductile region. And if a material behaves like this, say, for example, a material like steel, it doesn't matter, it will not fracture. If you reduce the load on it, the stress on it, then it might come back in a path like this. So in this region, actually, it is perfectly reversible. But if you go here, go up here, and then you can come back here. And there are different ways in which these stress strain, different routes that these stress strain paths can take. Now, let us think about using this concept of resilience, this concept of energy absorption, to see whether it can be applied anywhere else. So this is just one aspect of structural mechanics resilience, the fact that the elements must be ductile. And as we saw a little earlier also, if you have more elements that are required, then also you will increase the resilience. Like in that little picture of the mechano thing that I showed, if you have 6 members rather than 5, you have a degree of redundancy of 1. Now, this is a simply stiff structure, and this is a structure with a redundancy of 1. And also, we need to make sure that the shape of the structure is robust. But I will just look at this redundancy and this ductility. Now, we can set up a small sort of theoretical experiment. Think about a situation where you have 0 redundancy, that is just a single element, compared with a redundancy of 2, and then also one where you have 3 elements. And then also you have different levels of ductility. You have a situation where the element exhibits a behavior like that, another one where it doesn't have any ductility at all, and a third one where it has an intermediate ductility. And we can compare the energy under these curves. And we can use that as a sort of index of resilience. So one of the things that it shows here from this simple theoretical exercise is that you can have a trade-off between ductility and redundancy. So remember, ductility is a situation where you have abnormal behavior beyond a certain point, right? Beyond a certain point, especially at high levels of stress or strain. So here you find that you can have the same energy absorption, even though you have a low redundancy, provided you have a high ductility. And at the same time, if you have a low ductility but high redundancy, you can have a similar energy absorption. Now, I want to point you to an example where this concept has been actually utilized in infrastructure development, right? So this is called the smart tunnel in Kuala Lumpur. Kuala Lumpur is a city that has a lot of rainfall. And there is also a need for sort of a road tunnel because there's a lot of traffic in Kuala Lumpur as well. This is called the Stormwater Management and Road Tunnel, SMART. In situations where there is no rainfall, of course, the vehicles can use this tunnel in this kind of way. But underneath there is a drain that is there to take the storm water from one place to another. During annual floods, of course, this drain is full in this kind of way. Now, occasionally you might have a very large flood, something maybe you might call a 1 in 50-year flood or a 1 in 100-year flood. Now, this tunnel is designed to be shut down to vehicular access during that time. So I don't know whether you can capture that concept of ductility. When it behaves in this kind of way, it does not behave in the normal way. It behaves in a way that is somewhat different. But because of that, because you are shutting it down to traffic, it means that you do not need two separate tunnels, one for the vehicles and one for the rainwater. So this is a concept, if you can think plausibly, like George Collier was saying, then we can use these concepts from structural mechanics to actually plan our infrastructure systems. Now, because I live in Dehiwala, I want to bring you this example also. Now, this is actually taken from Google Maps, and you can see that this is the Marine Drive here, which until a little while ago was terminated here at Wasala Road on Melford Crescent here, right? Now, this is a picture that I have taken, I must confess, while I was driving northbound. And you can see in the morning traffic, there are two lanes driving northbound on this side of the road, as would be expected. But you can see on the other side of the road also, now this car is also driving northbound. So some of you may have experienced this in the recent past. So although the road is designed for two lanes to go northbound and two lanes to go southbound, in the rush hour traffic, only one lane is going southbound, right? So that means during those heavy stress or strain times, the road is behaving in a ductile manner. And that means you do not need, therefore, two roads. You can manage with one road. Of course, like I said, now they have built another road and the situation has become easier. But the moment you cross the Dehiwala Bridge, then of course, earlier also you had a Marine Drive and you had the Gall Road. So there was no need to exercise this ductility because there was redundancy. My personal view is that the whole world is facing big problems with regard to infrastructure, with regard to the great increases in population. And we need to make sure that we do not have too many redundancies. We have to ask ourselves whether we can think about these ductile modes of behavior in an analogical manner, like the smart tunnel in Malaysia. Like perhaps we did, we managed by having just a single road, but ensuring that it was sort of, behaving in a different way during rush hour. So in that way, I think we may be able to save resources. So this is one way in which infrastructure planners can learn some analogical lessons from structural mechanics. Right. Now, this is another interesting area also taken from my field of structural mechanics. And this is actually what we teach as a second semester students, still in their first year. Now, if you have a beam like this that is subject to bending, you can think about it that, in this beam, this top flange, as we call it, will be in compression, and the bottom flange will be in tension because it is getting pulled. So let us say that it has a cross section like this. And if you think about the stressors in that beam, so you will find that the direction of the stress changes because the top is in compression and the bottom is in tension. Now, we teach students that this is the most important formula you can ever remember. Now, in order to find the stress, what we do is to take what is called the bending moment, divided by the second moment of area, and then multiplied by this that thing called y, which is the distance to the point concerned from this neutral axis. Now, especially if you look at this part of this formula, there are two moments of area that are involved. One is to find this centroid, and the second one is called, in fact, just the second moment of area. Now, again, I'm trying to think analogically. Now, we have these moments of area in statistics as well. Now, the first moment of area is what helps us to find the mean. The mean is the point about which the first moment of area of this distribution is 0. The standard deviation is the number you get if you take the second moment of area about this mean. So in structural mechanics also, we have a first moment of area and a second moment of area. But in statistics, we not only have a first moment of area, we have a second moment of area, we have a third moment of area, which is called skewness, and we have a fourth moment of area, which is called kurtosis as well. So together with this student of mine, I tried to explore, is there any significance of third and fourth moments of area for structures as well? And this is what we came up with. So now, so when you have a beam that is subject to bending like this, we have what is called a bending moment, and then there will be what is called a rotation. So just like the earlier diagram that I showed about stress and strain, there will be a linear region like that, and there is what is called a plastic region like that. So imagine that this is the moment that is applied, this is the rotation that is caused in that beam, and this, and then of course the curve goes up and drops like this. This is called the plastic region. The difference between this rotation and this rotation is called the rotation capacity. The rotation capacity. Now it turns out that we can also find the standardized third moment of area for a cross section, and if we plot that against the rotation capacity of these different cross sections, we find a near linear relationship between the rotation capacity and this standardized third moment of area. Now we can even go to the fourth moment of area. Now here what we find is we do not use kurtosis directly, but we use what is called the excess kurtosis, the kurtosis beyond the particular limit that is defined by this equation. And once again, if we take the normalized excess kurtosis, this time not of I sections, but of closed sections like this, right? Tubular sections, right? Once again, we find that the rotation capacity is well correlated to this normalized excess kurtosis with a very good coefficient of determination, R squared equals 0.88. So we also find that, this rotation capacity versus normalized excess kurtosis has different slopes depending on the different types of cross sections. So if it is a rectangular cross section, then it has a shallower slope. If it has a circular cross section, it has a very steep slope. And in these elliptical cross sections, it has a slope somewhere in between. Now, this, of course, clearly this is not yet being used in sort of engineering design, but we hope it will have a future, and we are still working on this. But the proof of the pudding, as they say, is in the eating. Currently what is used is what is called the section slenderness. That is the diameter divided by this thickness, right? Or this dimension divided by the thickness in a rectangular section. So currently, the R squared value for correlation between rotation capacity and section slenderness is quite low compared to what we get for this excess kurtosis, where the fourth moment of area is concerned. So this is another analogical transposition that I would like to talk about. Now, the final one that I'm going to talk about is almost a bit implausible, and it takes us across different centuries from the 6th century BC to the late 20th century. And this is one of my favorite scientists of ancient times, Anaximander, who lived in the 6th century BC. Now, this is about an analogical transposition that goes contrary to the expected direction. I think you may remember when I talked about bridges being introduced to engineering students, we go from nature to structure. In other words, structural forms are inspired by nature. Now, can natural laws be inspired by structures? Rather implausible. But this is the theory of a fellow called Robert Hahn, who works at the Southern Illinois University, and we have published together, as it happens, in the Journal of the National Science Foundation. Right. Now, in ancient days, this was a picture of the cosmos. There was the firmament with the stars, all on sort of one canvas like this, one spherical canvas. And the earth, of course, had to be supported on these pillars of the earth. Now, Anaximander made two very significant theoretical statements, both of which in some ways are true even today. One, he talked about the free suspension of Earth in space, the free suspension of Earth in space. Now, this is a quotation about him made by Aristotle somewhere in the 3rd century BC, if I remember correctly. So Aristotle says, there are some who say that the Earth remains in place because it is in equilibrium, like Anaximander among the ancients. For a thing established in the center and equally related to the extremes has no reason to move up or down or to the sides. And since it is impossible for it to move simultaneously in opposite directions, it will necessarily remain where it is. So this in my opinion, is a very high level pronouncement, almost completely contrary to everyday experience, right? So he does not require these pillars of the earth, whatever they may be, to hold the earth. What he says is the earth remains in place because of its relative location to everything else. Now, where did he get this idea from, right? Now, Anaximander was living at a time when temple architecture was in its heyday, large Greek temples. And in fact, I got one of these Onassis Foundation scholarships to go and visit Greece. So this is a picture that I have taken myself. Now, you can see Anaximander also says that, and this is quoted by Hippolytus, that the shape of the earth is concave, rounded, similar to the drum of a column, right? So this is the way that these columns were constructed, made of column drums. So you can see that the equilibrium of each of these column drums depends on its relative location to other column drums, right? Vertically, it is quite clear. This column drum is supported by this one. Now, Greece, of course, is in an earthquake region, and not only must there be its vertical position, its horizontal position also depends on its relation to each other, because there are two reasons why even during an earthquake, these drums do not slip away. One is because of the friction. The other one is because of a small pin like this called an empoleon in Greek, that is made to connect these two column drums in this kind of way. So the argument is that perhaps his observation of structures actually made him to make a pronouncement about nature, and so the analogy works in reverse. The other thing Anaximander says is that the circle of the sun is 27 times the size of the earth, and that of the moon 18 times. The sun is the highest, and the circles of the fixed stars are the lowest, right? So rather than having a single canvas on which all the heavenly bodies are placed, Anaximander, proposed that space has depth. Of course, he got it all wrong. I mean, he said the stars were the closest, and then the moon, and then the sun. But at least he had this idea that there was depth where space was concerned. Now, how did he come across? How did he think about that? Maybe once again it was because of the temples, because the temples had inner areas and they had rows of columns in outer areas, and these are called dipteros temples because there are 2 rows of columns on the outside. Now you might think that this is rather fanciful, implausible, stretching the bounds of credibility. But it happened in the 20th century as well. So all chemists we know about Buckminster fullerene. So there was an British scientist called Harry Kroto who was visiting Rick Smalley at a university in Texas. And Smalley had an apparatus that could vaporize graphite, and using a mass spectrograph, they looked at the way that these atoms were arranged, right? So there was a remarkable stability in a cluster of 60 carbon atoms together, right? So they recognized that this was perhaps a new molecule, but they could not find a structure for that molecule. They tried to extend the structure of diamond, which is a what do you call it? I can't remember. Tetrahedral structure, or graphite, which is a planar hexagonal structure, as I recall, but none of it worked, right? So they say, so this is written in their paper in Nature. It says, thus a search was made for some other plausible structure. Once again, this word plausible, which one needs to use when we think about analogical transposition, which would satisfy all the sp2 valences. Only a spheroidal structure appears likely to satisfy this criterion, and thus Buckminster Fuller's studies were consulted. An unusually beautiful and probably unique choice is the truncated icosahedron depicted in figure 1. So this is given in their paper in Nature. Now, there is a person who has written about this called Addison Wesley, and he says that both Harry Kroto and Rick Smalley independently visited the US Pavilion in Montreal somewhere in, I think in 1978 or something like this. This discovery was made in 1985. And he conjectures that this image of Buckminster Fuller's dome that both of them had seen independently, and of course maybe through other literature as well, is what inspired them to think about this structure. So once again, you have inspiration from a structure in order to propose some kind of natural phenomenon like this, which is Buckminster Fullerene. So I think I will stop there, but one more slide perhaps. And this is to celebrate Kepler. Now, Kepler also was a person who used a lot of mathematical analogies. Now, in his book, Mysterium Cosmographicum, he was always a person who looked for this kind of analogical sort of relations, especially with respect to mathematical analogy, right? So now by that time, there were 6 planets that were discovered, and he was interested in astronomy and in fact, astrology as well. And he thought that the orbits of these planets, that they bore some kind of relation to what he called these Platonic solids. That is, equilateral cubes, tetrahedron, dodecahedron, icosahedron, and octahedron. So if you take like the outside one, the cube, for example, you can think of a sphere that circumscribes this and a sphere that is inscribed by this, right? So this is the sphere actually that circumscribes this. Now the sphere that is inscribed by this is this one that you can see here. So he's arguing that the orbit of Saturn will be, and the orbit of Jupiter will be in the ratio of this sphere to this sphere, right? And then it goes down to the other Platonic solids like this, right? And in fact, where observation was concerned, now Kepler found that the observations up to that time were within 10% of this rule, 10% of this rule. And he thought the 10% discrepancy was because of experimental error. Of course, Kepler was completely mistaken in this idea, right? So sometimes analogy can lead us into sort of, in wrong directions, right? But the desire to see elegance in the science that he did was what made it possible, in fact, to discover some other laws, also elegant in themselves. So what happened was, this fellow called Tycho Brahe, who was a very prominent astronomer, he read what Kepler had written in this Mysterium Cosmographicum. And he said, okay, well, this is an interesting idea, but it has to be verified by observation, verified by experimentation. It's a very fundamental idea in science. Okay? So he gave Kepler the orbit of Mars, his observations about the orbit of Mars. So far from being spheres, Kepler discovered that they were in fact ellipses, not only of Mars, but of all the other planets. So the first law is that planets circle the sun in elliptical orbits, where the sun is at one of the foci. It's at the focus, one of the foci of this ellipse. The second one is that a planet sweeps out equal areas in equal times. And the third one is, you take two planets, and if you take their the major axis in the ellipse, then the ratio, the major axis cubed is proportional to the time of this traverse of the planet around the sun. So beautiful, beautiful laws. The law of orbits, the law of equal areas, and the law of harmony. So there is a book that is written here about the way people do science, especially physics, but now gradually in biology as well, saying that it must be beautiful. And all these equations that have been developed are in fact very beautiful equations because they are very, 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 very compact, right? This is Fick's law of diffusion, which I use sometimes, right? And even if you look at that bending example that I gave, where this formula was presented, if you think about the derivation of that formula, which I'm not going to go through, in the process of deriving that formula, suddenly you find that one of these terms is in fact the second moment of area. Now, the second moment of area is a completely independent mathematical construct. It has nothing to do with the stress in the beam. But when one tries to relate the stress in this beam to the moment that is applied externally, suddenly one finds that there is a second moment of area coming out in this term, which is what makes this calculation so easy and elegant. So Eugene Wigner has talked about the unreasonable effectiveness of mathematics, right? So in conclusion, what I would like to say is, whatever way science is conducted, and if you read the philosophy of science, you have inductivist methods that start with experimentation. You have deductive methods like falsification that starts with theoretical postulates. You find that there is always an interaction between theory and experience. So what we are doing in analogy is we are generally using theory from one area and correlating it with experience from another, right? So for example, network theory, we are trying to apply to the connectivity of trusses. Sometimes it works in the other direction as well. So we have experience of Greek temples, and then we come up with a theory about the cosmos. So these are kinds of the kind of linkages that one can have, and I think when we do science, we need to always be mindful of these two domains, theory and experience. Try to make a link between those two, and then in the process try to use analogy as well, because sometimes you might come up with some very creative discoveries. Now there are some things that I have to do. I have to thank certain people before I stop. So once again, I would like to thank the Sri Lanka Association for the Advancement of Science for inviting me to do this lecture and bestowing upon me this great honor. I would also like to thank the Soysa family, just with respect to some personal connections. Of course, I said we knew Professor Priyan Soysa's sister's family, Dr. Riley and Manuel Fernando. My sister, I think, was at school with one of the daughters, and then also worked closely professionally with another. I think my wife played the organ for the wedding of another daughter. So it's very nice for me to give this oration. I would like to thank the University of Moratuwa, where I had a 40-year career, and a university like most of the universities that gave me freedom, unfettered freedom for scientific inquiry and exploration. I would like to thank this journal that I was an associate editor of, because a lot of these ideas I have got through interactions with that. These are some of the people I have collaborated with. I would like, in closing, to pay a tribute to Tony Senviratna. I invited him for this lecture. I do not know whether he's here. Tony was a person who, in my late teenage years, could best be described as a youth counselor. He worked for an organization called Youth for Christ. Actually, it was a Christian organization. And far from telling us that, Christianity had to be accepted by faith, he made us question everything, Christianity and everything else about life. He later on went on to become the National Director of Habitat for Humanity Sri Lanka, and also the Deputy Chairman of the National Child Protection Agency. So Tony Senviratna, I owe a great intellectual debt to him, although he did not have a doctorate, or he did not even have a first degree, but I owe a great intellectual debt to him. So I would like to put that on record. My father, of course, did have a PhD, as was mentioned earlier. He worked in the Department of Agriculture, and I'm sure he had a great influence in my trying to pursue this kind of academic role. I'm sure he was president of Section B or something like that. I haven't actually found out the actual year or whatever. So that had a great influence on me. Because he was in the Department of Agriculture, he had to be out of he had to be outstationed for a large number of years, and my mother had to look after the family. So I'm very grateful for those early formative years. I would like to pay tribute to my nuclear family. Shanti, like I said, she has always been very supportive of my career, although she has played very responsible and important roles in life. She is a concert pianist of no mean repute, even though I say so myself. And for 11 years, she was principal of Methodist College. So she has made great contributions to society, but has always supported me in whatever I have done as well. Hopefully, I have supported her also. Ashwin, our elder son, is an engineer who has followed my footsteps, I suppose, in a way. Sanjit, our younger son, is a lawyer, but he's philosophically inclined like I am. So thank you very much. Thank you for this opportunity, and I will stop there.
Thank you very much, sir, for very inspiring oration. I had never thought of the limit to growth the way you have explained just now. You never stop inspiring us. Thank you so much. Finally, we come to the conclusion of the Bernard Soysa Memorial Oration 2021. Thus, to formally deliver the vote of thanks to conclude the event, let me invite Secretary of the General Research Committee of SLAS, Dr. Kumudu Senaviratna. She is a senior lecturer of the Faculty of Education, University of Colombo. Over to you, madam.
Thank you, Professor Shiromi. Our invited orator for the Bernard Soysa oration for the year 2021, Senior Professor Priyan, the General President of SLAS, and all the family members of the respected late Professor Bernard Soysa, and the respected members of our SLAS, and all the distinguished gathering here with us. Good evening to you all. And on behalf of General Research Committee of SLAS and the SLAS Council members, I wish to express my deep sense of appreciation to the family members of all respected Professor Bernard Soysa for their continuous contribution to the success of this event of the SLAS in the year 2021 too, and normally it happens every other year. Next, I take this opportunity to extend our gratitude to Senior Professor Engineer Priyan Dias, our respected orator today, for accepting our invitation to be the Bernard Soysa orator for the year 2021, and sir, for delivering an insightful oration on interdisciplinarity through analogical transposition. And the way you approached your title of this oration, introducing us the different perspectives of disciplinarity, was highly commendable, Professor. I believe your clear elaboration on system dynamics for concrete durability would be of greatly important for most of our audience. And you also made us aware of how we could success in planning infrastructure through analogical transposition. Not only, sir, the historical introduction of analogical transposition under the theme from structures to nature and the ideas of Anaximander in this regard was highly interesting, sir. Therefore, ladies and gentlemen, I hope the audience would wholeheartedly join with me to congratulate to Senior Professor Priyan Dias for the great contribution he rendered to make this event not only a reality, but also very fruitful. Thank you, Professor, again. And I also extend my gratitude to the General President of SLAS, Senior Professor Sumedha Jayanetti, for mentoring us in organizing this valuable event of the SLAS year calendar, and which was a great encouragement to us making this event a success. And our sincere thanks also goes to all the supportive staff at the SLAS head office, especially for their untiring support in coordinating this event, having conversant with the family members of the Professor Bernard Soysa, and also for getting done the medal in this regard. And I also take this opportunity to pay my deepest respect and appreciation to all the members of SLAS, especially all General Research Committee members for the year 2021 for the strong support they made to carry out these initial activities of this event. And my special thanks goes to Professor Udeni Navagamur, the chairperson-elect for the year 2021, GRC chairperson, for his untiring support in coordinating with our respected orator, Senior Professor Priyan Dias. Last but not least, and with boundless thankfulness to our chairperson GRC for the year 2021, Professor Chamari Hettiarachchi, for her leadership in making this event a great success. And again, last but not least, my sincere thanks also goes to Professor Shiromi Karunaratne for mastering today's program in a commendable manner. Thank you, Professor Shiromi. And also, on behalf of SLAS, we are grateful for our audience for joining with us today with this program. Without you all being, this event would not have been a success today. Thank you again for all. Have a nice day. Stay safe and blessed.
All good things should come to an end. Ladies and gentlemen, thank you very much for joining with us for the Honourable Bernard Soysa Memorial Oration 2021, delivered by Professor Priyan Dias. Have a very pleasant evening.